This conference will now be recorded.
Good morning, everyone. Good evening, everyone. Good afternoon, everyone. Wherever you are, whichever part of the world you are located at now. So, is my voice is? Let me ask someone. Can anyone can respond only one at a time? Is my voice is audible?
Yes, sir.
Yes, sir.
Okay. So it is clear, right?
Yes, sir.
Yes,
Okay.
sir. Yes,
Okay.
sir.
Thank you. Thank you. Thank you all. So. So today we'll be discussing about the unknown input observers for state and fault estimation. So before going to this unknown input observer for the state and fault estimation, we will continue our discussion on how to reduce the chattering in the sliding mode in a minute. That's what I promised in the afternoon, that I shared you a pic and I told you that we'll be discussing that one. So this is already, I sent you the slides as well. So this is
Sir,
what you can
voice
see.
is clear, but can you please increase your volume?
Sorry.
Voice is clear, sir, but volume is very low compared to last classes.
Okay, let me keep my earphones on. Is it better now? Hello, is it better?
Yes, sir.
Not
Yes,
much.
sir.
Madam, maybe you may have to increase your volume from your side. Could be, because yesterday also you have to use the same mic with the same.
Now it's okay.
Sir, voice is not clear.
Now, is it better now?
Yes, sir.
Okay.
Yes, sir.
Okay. So we will have we'll start our discussion now. So what yesterday we have seen the major problem with the sliding mode control, and there was a lot of discussion on the chattering aspect. So I will tell you in a minute how the chattering can be reduced. There is this is quite ad hoc way, and I remember Christopher Edwards has while delivering our project to the Airbus, we use the same small trick. It is a kind of heuristic way to reduce the chattering, because sliding mode has all the good properties for for everyone, but as compared to all other different controllers, so it has very good properties, but the problem here is the chattering. So we will see now how one can reduce the effect of chattering in a minute. So you can see that signum or sine function, this is the one which is mainly responsible for the chattering in the sliding mode control. Signum function can also be represented, this is more or less the same, as gn of x equal to x by norm of x. So this is the 2 norm of x. So this will exactly, give the equivalent of the signum function can be written like this. So this is the inbuilt code of the signum function if you see the MATLAB. So the approximation here is, if I write the signum function, as like this, x by x norm of x plus some small tiny value of delta. The delta is very small positive trade-off value. I will tell you what is this trade-off about. So this is the small trade. I will tell you what is about. So in the code, what you might have already seen uh, the sliding mode control, even the observer as well. We might be using some sign terms. So what you had to do is you had to replace this USMC minus C into XT row, keep it the row same, where the sign is there. What we have seen, sign of sigma is a sliding surface. So you just replace this sign of sigma by norm of sigma plus 0.001, and this is the delta what I have chosen for my particular application. And what will be the real time implication of this delta when you use for the practical applications or other things. We will see. In a minute, I'm going to. So this is the one what we have seen, that sliding mode in presence of sinusoid uncertainty. We have seen that the good properties, this convergence is happening fine, the sliding surface is fine, and this is the what the main troublesome. So this is the quite high frequency chattering, and a lot of people were some concerns about the chattering if you use the power electronics or any of the devices, how to compensate this one, because this is not the good thing. High frequency phenomena, sometimes it might uh, you know uh, it might damage your device as well. So the approach what I told you now, the sigmoid approximation, if I use that one, then I can able to get these good properties. Now you can see that it is no more chattering. And I will give you the live demo as well. So this is the same, everything is the same, only the control I changed. The control what, this, I use the second control law. So in the second control, if I used, so just what you have to do is you have to replace this with this. So it will give you this nice results. And I will show you small demo as well, what I did. Yeah. So this is the same code what you might have seen. I have added another switch here, just to switch between the USMC is the one which uses the everybody's name, which uses the signum function, and this is the approximated signum function. If I double click this one, you can see the same thing. USMC is the one with the sine term, and the USMC one is with the sigma term. So now if I just go here, and I will show you again, if this is for the first one is for the linear term, with the linear terms, if this disturbance is on, you can see that so this is not the what I want. It is not able to reject the disturbance. So this is with the inverter. And now I have connected to the SMC. There are two SMCs, one with the sine function and another one with the approximated sine function. So now I am operating our old sliding mode control with the sine function, and you can see that the control is highly chattering. There is the effect of chattering. And now I used a 1 minute modification in that one. I just replaced that sine formula with the sigma by norm of sigma plus delta. You can see that now I have switched to the another one. And now if I'm clicking this one, first of all, I have to see whether there is any compromise here. You can see the states are very fine. Both the states are converging. And this is the control signal. You can see the control signal is also smooth. So this is quite realistic for the real life systems. But what is the problem here? So what is the trade-off here? The trade-off here is something like this. So this is the what you have seen. If I plot, you'll be getting like this. So this is the one with sine, exactly the SGN function, and this is with the approximated sine. And you can see that it is quite smooth. But what is the trade-off? Why we have selected 0.001? So the trade-off, you can see that this is the sigma. So since we have selected 0.001, there is some small error here. You can see that the error is from between 1e minus 3 and -1e minus 3. So this, whatever the denominator we are adding here, you can see that this whatever we are adding here, the same thing. So instead of going to the zero, the sliding surface, there will be a small bonds. So it will settle in that bond. So this, how to select this one is based upon your plant. If your plant parameters are very small, like if it is in the milli micro, then you can select this as small as much possible. If your plant parameters are very large, then you can this delta value can go to very large values as well. So there is a trade-off. So I have selected 0.001 1 milli, and you can see that it is 1 milli is the one, but nothing significantly. You can see the difference in the plots. So this shows that sliding mode control is a good choice for several real life applications because it makes the system independent, or it actually decouples the disturbance or the faults from the system performance. So as soon as the sigma reaches to zero, then automatically it makes the insensitive to the disturbance. So it doesn't matter what how much disturbance whatever you add, your sliding mode control will ensure that provided it should have the bonded, and only the bonds we should be aware of. One can always argue that I will select a very large value of bonds and I will ask my sliding mode control to to work for all world problems. It is not like that. So if you are selecting very large value of the bond, maximum value of the bond, so your controller will become conservative. So conservative in a way that by one controller you are trying to from zero to infinity kinds of disturbances if you want to deal with them. Then again there will be some issues in the control action. So there is a compromise based upon the problem at your hand. So this is the one. So this is a sliding surface sigma. You can see that 0.001 what we have selected. It is reflecting here. So now what I want from you is you take 10 minutes of time. Please implement. This is very, very much essential for the people who want to really dig into the sliding mode. So this is the small trick which generally people don't know, and they will go for higher order sliding mode and other things. But industry, it is working here, though it is heuristic in way. This adding that sigma, it is working. So when we gave this solution to some industry, then it doesn't matter to them. As soon as it is working and it is very reliable, it doesn't matter to them what kind of control you are using. If it is proven, and if you can prove on prototype, and if they have certain test simulator or some hill system, if it is working fine for all kind of different, they will do all kinds of tests. Then they will, if it is certified, then they will go for it. So this is a small approximation what we have done. So the similar results, more theoretically intense, higher order sliding mode, and so on. So it has some good properties. So this chatter can be reduced there as well by using the higher order, but at the the burdened computation complexity. However, this is a small trick what one can use, though it is an heuristic trick, but it will work for practical systems. If you want to really implement for any power electronic devices, and you don't want this high frequency chattering for your control to see, for a system to see, then obviously you can use this small thing. So this high frequency chattered signal has now converted to very kind of a smooth sinusoid signal. So what I will say that you just try to implement this one for another 10 to 15 minutes. We'll meet at around, now it is 18. So we'll meet at sharply at 7 o'clock. You do this because this is very much important. So what you have to do, you have to, that USMC, whatever is there, you just replace with either you remove this one as well, USMC, the same thing, only with the sign of sigma with this one, sigma by normal sigma plus 0.001. And as soon as if you get the result, just take a screenshot and send it in WhatsApp or in the chat box. So we'll meet at 7 o'clock. So do this one. This is very, very important. Thank you. As soon as you receive the results, please post it in the WhatsApp group. I mean, after telling so many times, people are not using this the reference number hash dash your name. I might have to forcefully remove around 10 to 15 such So please, all of you, please change your names to your roll number, your reference number dash your name. Sharad Babu, please be on mute. SSS triple S or sulfur.
Yeah, muted, no? Sir. Hello? Fine.
Hello.
It's okay? Hello?
Sir, please be on mute, sir. Sharad Babu, please be on mute. Okay, so if any of you have received the results, the better results, please post it in the either in the WhatsApp or in the thing. Anyone? Yeah, good. I can see Bhanu Prakash has received. Syed Abdul Mujir, Nedumal. Still, sir, still chattering. Nedumal, I think you might have done something wrong. If you can share your, if you share here your
Sir,
the Simulink diagram, then I can see.
yes. Sir, actually, the only change what we have to do is in the control part, we have to change that command now, sir. That is the only change we have to do.
Yeah, yeah. The thing already what I already have that PDF file. It is there, right? The same thing.
Yeah, yeah, sir. I will be
Yeah.
sharing that link to the to your chat box, sir, or I have to send it to mail, sir.
No, you can email me later. Maybe there could be. You just share the
Okay.
screenshot here.
Yes, sir.
Shivaramarav has got good.
Hello, sir.
Syed Mujir.
Hello, sir.
Syed.
Yeah, yeah, sir. Tell me,
Yeah,
sir.
yeah. Yesterday it was
Wait
your
a minute, sir.
query, right? This was the problem. Now you can see the thing.
Sir, I did not get you, sir. Can you repeat once?
No, yesterday this was the
Hello, sir.
query from you, right?
Yes, sir. Yes, sir. Yesterday I was asking. So, yeah. Yes.
Yeah, yeah. So this is a small trick. If you can,
Yes, sir.
which will give you the real-time implement. This sliding mode can be, real-time. You can implement if you use this particular small
Yes.
trick. The whole chattering has gone.
Yes, sir.
Nedible has some issues.
Okay.
I don't know. I have to see. Nedible, can you please double-click your sliding mode control and just send me the screenshot? I will see.
Hello, sir.
Yeah. Hello.
Sir, where we need to change the code, sir? Which block?
That control block. Control block.
In sliding mode, UN sliding mode code, sir.
Yes. 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 That is
UN
the only place where one has to change.
SMO control, sir.
Yeah. The same thing what I shared you in the PDF. It is there, right? Two lines. One line you have to replace with another, and you will be getting the results.
But the first line is not in this code, sir.
Huh? Maybe you can see later. So we'll start our discussion on on unknown input observer. I assume that maybe Nedimal, I have seen it looks okay to me, but I have to see in very detail what is the mistake there. Uh, yeah, I can see Nedimal. You have kept 3 zeros. You keep 2 zeros. If that is also not
Yeah,
working, there is ah no. Okay, I will get back to you later. So let's start the meeting so that it will be useful for everyone.
fine,
So now
fine.
what we will be discussing is today the concept of unknown input observer, and we will see what is this unknown input observer and why the screen is not visible. Is my screen is visible, right? Yeah,
Sir,
I
yes,
think it
come
is
on.
visible. Okay. Fine. Just give me a minute. Something has happened. I will just stop the screen here. Yeah, now it is okay. Just I'm sharing my screen. Okay, so thank you for waiting. So now what we will discuss here is the unknown input observer. First of all, I will tell you what is this unknown input observer and why it is required, and what is the philosophy behind this unknown input observer, and then we will go to the next part. Okay, consider the linear plant x dot equal to ax plus bu plus capital E into d of t, where d of t is a unknown input. That means you don't know what is this d of t. This d of t can be a fault, can be an uncertain plant, because x dot equal to x plus b you are trying to approximate with some linear plant, and the non-linear you can represent, you can assume that d of t as a non-linear plant, and it could be any noise, process noise, or it could be fault, or it could be the disturbance, or any of these things. So this all things I say it is a d of t, and this e, I will tell you what is this e, and y equal to cx. I assume that d is 0, capital D is 0, and d of t is unknown disturbance, and a, b, c, sorry, there is d is 0 here, so are known matrices. There is an assumption that capital E is full matrix. This E should be known. Instead of this D, please read it as E. This is the E. Uh, Assumption is that E is a full rank matrix. This is quite due to the generality. We can always assume that E is uh, full rank matrix. If it is not full rank, the meaning of the full rank is the standard matrix theory. If you are aware of, the total number of linear independent row, or the rank of the particular matrix is equal to the if the rank of that particular matrix, how to find the rank is again question. You can find the determinant, and from the determinant you can find out if it is not equal to 0, then it is a full rank, and so on. So it is quite you can do it easily. If it is not full rank, then you have to do certain matrix decompositions, either by using the QR decomposition, or there are various decomposition, where what you have to do is you have to split this E into d of t into 2. So where E1 and E2 into dt. So E1 is a full column matrix, and E2 can be considered, E2 into d of t can be considered as a new unknown input. But in most of the cases, you don't have to go for this thing, because E in general is full rank matrix. And whatever I'm discussing, for this particular talk, I have taken from the reference by Chen and Patton. And Chen and Patton are basically Patton is a supervisor, once upon a supervisor of Chen, and they are at the University of Hull. I don't know now where they are. So this Patton has, I had an opportunity to meet with Patton for some collaboration sometime back. This Patton has contributed very much in this area of the fault diagnosis, fault detection, fault tolerant control, and so on. He's a very old, 80 plus. So what is the purpose of the UIO? The purpose is to estimate the states in such a way that the estimation error vector approaches to 0 asymptotically, regardless in the presence of the unknown disturbance, which is regardless in the presence of the unknown input, which is disturbance in the system. That means there are two purposes. The first purpose is we have to estimate the total states even in the presence of the disturbance, regardless of the disturbance, whatever is the disturbance, but you should be able to estimate the states accurately. That means the estimation error between the states and the estimate should go to 0. That is one such the purpose of UIO. Another purpose is to very easily you can reconstruct the unknown fault as well. That aspect we will discuss at after some time. What do you mean by the reconstruction of the fault, or the fault detection, or what is the purpose, and all other things we'll discuss. For the time being, we assume that our purpose is to estimate the states of a plant in the presence of unknown disturbances. You don't know what is the unknown disturbances. It could be anything. It could be, It could be sine wave, it could be cosine wave, it could be noise, it could be external disturbance, and so on. So we will see what is this. The first step here is we have to select the observer structure like what we have selected yesterday. It has two parts. One is the linear part, and the another one is the non-linear part. The linear part is very much similar to the Leuenberger observer, but the non-linear part has the sine term. So here also for the unknown input observer, so we are selecting two different. So this is the observer structure. You can see z dot equal to what I'm interested. I am interested only in this x hat. X hat is the estimation, is the estimated value of the states x. Okay. So what is this x hat? X hat is nothing but z plus h into y of t. So to get this z, I have to integrate this z dot. I'm coming back to this point. What is this z dot? To get this z, I have to integrate this one. This h is unknown, and this y is the output of the plant. We know what is y. From the plant we can get it. So the matrices f, t, k, and h are to be designed to decouple unknown input from other design requirement. So that means unknown is this f, we don't know. We don't know this t. B is known to us from the plant because x dot equal to x plus bu. U control input is known to us. We don't know what is this k. This is the output of the system, we know. So from this, how to get this x hat is something like this. So this is my system. The input. So as once if we start designing the observer and controller independently, as we discussed, due to the principle of separation, you can design two different stable controller and observer, and then if you combine, then also it will have the stable properties or good properties of both of them. So here the input is coming from external this thing. I assume that this control input from somewhere it is coming, maybe from some controller or from somewhere else. So that is coming. And the system is perturbed with unknown input, which I call it as a disturbance. So you can see that this d of t is the disturbance. I will explain you this particular block diagram. This x hat, if you see this x hat, this x hat has two different signals coming in. Two signals are getting added to generate this x hat. One is h into y of t. Another one is z. So that's what you can see, that x hat equal to z plus h into y. H is this gain is multiplied with I. So this signal is hy plus z. So that is my x hat. The second thing is this z dot. So this is my z dot. So this particular block is my z dot. So z dot, what is happening? This z dot, I'm integrating. If I integrate, I will get the z. So this z dot is nothing but f into z. So z is coming from here. So this is f into z. The first term here, f into z. The second term is tb into u. U is coming from here. This t into b getting added. And the third term is k into y. So from the plant, it is coming the k, and it is all three of them are getting added to generate this z dot. So this is the whole structure of the unknown input observer. So here what I'm getting is the complete states. So now the problem here is how to find this F matrix, T matrix, K matrix, and H matrix, such that whatever you are estimating here, it will be decoupled from this unknown input. So that means the effect of this state estimate will be completely insensitive of this unknown input. So we will see what is this one. So consider again the estimation error. The estimation error E equal to x of t minus x hat of t. So x of t, you can get it from the plant. This is the plant states, and this is the estimated states. So I have to design the estimator in such a way that the error dynamics E dot should go to 0. If I substitute this x dot from here, the derivative, and x hat dot from this particular equations. So how do I get x dot? Since I have the x, if I take the derivative, I'll get the x hat dot, and so on. So if I use the x hat dot, so if I subtract x dot minus x hat dot, which is nothing but E dot, and if I do substitute, if I do all the substitution, then it will look like this big equation. So it is better if you take the pen and paper, and if you can do what is E dot equal to x dot minus x hat dot, You substitute x dot from x from the plant and x hat dot from your state estimator, then you'll be getting these things. Where I will assume that k equal to k1 plus k2. So now the philosophy, I have to ensure that these error dynamics are stable. How do I ensure these error dynamics are stable? If and only if and only if all these terms equal to 0, and then additional term if it is added f into e of t. So my aim is to ensure that my left hand side, the right hand side should be f into e of t. In a very simple case, if it is a scalar case, if this f is negative, suppose -1, so what is this e dot equal to minus of et? So if I take the solution of this first order differential equation, if I assume that it is a scalar, then it will be exponentially decaying function. So and hence it will be stable. If the error has so many vectors, like if error is a vector, that means e1, e2, e3, which is, if it is nth order system, fifth order system, so 5 error terms will be there. So how to ensure that this particular stable error dynamics? For that one, this F matrix I have to select in a such a way that all the eigenvalues are on the left of West plane. If all the eigenvalues are on the left of West plane, that means my system will be, the complete system will be stable. So E dot equal to F into E of t. So I have to ensure. So the trick here is, all of you please listen, the trick is very much important. If I want to make this particular term, which is the disturbance here, so if I select hc minus I into E, or rather hc minus equal to 0, if I select this particular term as 0, then what is going to happen? This effect of this d of t will be completely, you can neglect from the error dynamics. And similarly, if I select t equal to 1 minus hc, if I select t equal to 1 minus hc, so if I select this particular part equal to 0, since c is known to us, I is the identity matrix, E is also known to us. If I equate this particular part to 0, then since C is known, E is known, H is unknown. So one unknown and one equation. If it is n, H has n components. If H has n components, then nth order system and n variables, then unique solutions you can obtain. So this particular term will become 0. And interestingly, since if I make this particular term as 0, E is known, C is known, so H I can find out. So now the next thing is I have to make this particular term as 0. So what I will do, t minus I minus hc equal to 0. So since h is obtained, we have the information from here. I will substitute. So my t equal to I minus hc. So I have the t information as well. So similarly, I will keep on going. Next, what I will do is I will make this particular term, this particular whatever the big term, equal to k2. Then k2 minus k2 will get cancelled. This particular effect will get cancelled. Similarly, if I select f equal to this particular things, a minus hc, a minus kc, then this term will get vanish and this term will become f into e. We'll see in the next slide what is going to happen. So though this looks bit numerically very intense, but just I want to give you the flavor how to select the stable error dynamics of the system. So this is the stable error dynamics of the system. What I want is e dot equal to f into e. So what I substituted this whole value as f. So now e dot equal to f into e. So since this is also f, so this f and this minus f will get cancelled. So the effect of z of t can be nullified. And then k2, what I have discussed earlier, k2 equal to, this is again f into h. If I select k2 equal to fh, this is fh minus this whole term is f into h. So this term will also vanish. And if I select t equal to I minus hc, this one as I minus hc, so this term will also vanish. And eventually, if I select hc minus I into e as 0, this whole term will get cancelled. This term will get cancelled. So eventually, if I substitute these values, so my e dot will become e. So what I'm doing here is I'm selecting the design parameters f, h, t, k2 in such a way that I'm forcing the errors dynamics of a system to be stable, and hence error will go to asymptotically, it will go to 0 as t tends to infinity. So this aspect, so that is how you have to select a and other values. So now what I will do here is so this is till now the state estimation. So what, since the error will go to 0, it will ensure that x will go to x hat, and hence my state estimates are x hat. It will have the accurate values. So now this is about this is completely about the state estimation from the unknown input observer in the presence of unknown inputs. So now the idea here is, how do you estimate the noise? Noise or disturbance, D of t. The purpose of estimating the disturbance is very much important for as far as the fault tolerant control, or if your system is prone to fault or system is prone to faults, then the concept of this fault estimation is very much important. For example, in the very naive case, some fault is happening in your system, some fault is affecting your system, and if you know that fault, what is that fault, then automatically your control can take action based upon, if you have the good information, then you can cancel out that fault, and you can eventually have the fault-free kind of system, provided if you estimate the faults exactly. So now here is now next I will show you with the tiny equations then how to estimate the faults as well. So what you can see here is y equal to cx you have seen. If I take the y dot, then this is nothing but c into x hat dot, taking the derivative on the both the sides. So what is my this equation? The unknown input or disturbances can be estimated as y dot. What I'm saying that my state estimate, instead of the states I am replacing with the state estimate, because if I keep y dot equal to c into x or so on, c into x dot, so x is not known to us, so instead of the x I am replacing it with the estimates. So if from this equation you can see that, and later I will replace it since y dot with the y dot hat as well to have more accuracy. So what I'm doing here is I'm just manipulating this particular equation. That means I'm keeping this term in one side, ed, and all other terms on the other side. So what is going to happen if I keep this in one side and all other? So this will become y dot. I will replace y dot with y hat, assuming that the estimate is the best one. Y dot minus ca x hat minus cb u. So if all the terms are going on the left hand side, on one side, then here what will be your left over with? Ce into d of t. So now what I will do, I will pre-multiply ce. This particular symbol is a pseudo inverse. That means if c is not the square matrix, then how to find? Penmurray, excuse me, Penmurray pseudo inverse is there. I will not be discussing much into that one. For the non-square, if it is square matrix, then directly you can take the inverse of this one. So d hat is this one. So d hat is the estimate of the disturbance or the unknown input. So what we have discussed now, we have discussed by using the unknown input observer how to estimate the states irrespective of the external input, which is the disturbance, irrespective of the disturbance. And the second thing is we have seen how to estimate the disturbance as well. So I will show you this simulations. So I have taken the same plant from the Ron Patton and Jianqi Chen. A matrix is given to us, C matrix is given to us, E matrix is also given to us. This E matrix tells about the uncertainty or the which channel is more prone to fault. So that you should be aware of, because if you have 10 particular 100,000 states in a particular system, you should be it is good to know which particular state is more prone to faults. Then accordingly you can work for that one. For example, if you're going in the bike, one of the faulty things is either it could be the injection of the petrol, or whatever it may be, or if it is some engines. So based upon various input channel, you should know which are more prone to faults, and accordingly this E can be selected. Some channels can be more faulty, then accordingly if you think that all channels all states can be faulty, then you can use this E value with all non-zero values. But you can use different values. Suppose if one is more prone to fault, if 10% of your state gets perturbed due to some reason, then you can keep this E as according 0.1 and so on. So that's why you have to select. As I assume that this is the plant which is given to us. Now the aim is to design the unknown input observer to estimate the states and the disturbance as well. So how to do this thing? I will show you. So this is the small tiny code, the Simulink diagram what I have developed. So I will try to compare this with the Simulink diagram. Sorry, with the block diagram what I have shown. Just give me a minute. I will just copy and paste that here. Okay, so now it is ready. So I'm sharing my screen now. Yeah. So now you can see, although it might look bit tiny, you can zoom your screens if you're using the mobile or accordingly whatever it may be. You can see the same thing I have implemented here. So you can see the plant to the plant. There are, the plant has states x dot equal to x plus b. This is the complete plant. And in our case, this b is 0. So this u term is 0 in our case. So there is no point in calculating this tb because b itself is 0. So now what is happening? So this is the two types of disturbance or unknown inputs I have considered. One is the sinusoid one, and the another one is the what I can say that unstable ramp one. So this is the switch I can switch on for various disturbances. So this is my plant. So this is the system. From the system, the output. So I am only worried about this output. I don't know what is going to happen with what is happening with the state. Only the output through some sensors is available. So what is happening in this output? So this is my this particular term z dot. So this is what is happening here is this k is getting multiplied with y. So that's why you can see that k is multiplied with y, the same thing. And this integrated the same. Then this f, whatever you are getting this z here, this z dot here, z here, that f into z. So this is getting added. The same thing you can see. And here you can see that the state estimate. So this is my state estimates, the complete state estimates. So what is it? It is nothing but h into this y, h into y plus this z. So z plus h into y. So this is what I'm getting here, the state estimate, and I can say that this is the unknown estimated states. But the next thing what I need is the second case. I need the y dot hat. Y dot hat, how I'm getting this is x hat. So what I'm doing here is this x hat, c into x hat will give the y hat, and this small tiny things what you are seeing here, it is a derivative action. Okay. So this small tiny thing what you are seeing here is the derivative d by dt, and what here I'm getting is from here I'm getting x hat into c into x hat is nothing but y, and here I'm getting a y dot. So this is y dot is going here, and x hat is also coming from the plant. So based upon the x hat and y dot, I'm going to estimate this disturbance observer. So this is exactly the same thing. So this is the one. If I copy and paste it here, so you can see this one, whatever this particular expression, it need y hat dot. So y hat is coming here, c into this is x hat into c into derivatives. This is y dot I'm getting from here. C and a are already known to us. This is the plant parameter, and x hat is also required. So x hat is coming from here. In our particular case, this since the u is 0, so this particular term will not be there. And e is known and c is also known to us. So if I do like this, so this is the code: A matrix, C matrix, E matrix. This is known. Fk and H, by using the formula what we discussed, you can easily calculate this Fk and H. So this is the parameter file. The first step is you have to run this parameter file. And this is my plant. So my plant is x dot equal to ax plus bu plus ed. However, you can see that since the u is 0, so this has become there is no u terms, x dot equal to ax plus bu plus cd, and y equal to cx. This is my plant code. So inside the plant, you had to dump this code. And this is the disturbance code. If you see the disturbance code, if you see this disturbance code, so PINV, so as I told, Pan-Murray inverse or pseudo inverse is P-in-Y because C into E is not the square matrix. So this is the disturbance input. So this is the estimate of the disturbance or disturbance hat, D hat. So disturbance hat is P inverse into C into E into y dot hat minus C into A into X hat, C into A into X hat. Since this B is 0, so this term is not, it is not there with us. So this will give us the disturbance estimate as well. And these are the results of one such case. I have given the sinusoid as the unknown input. So you don't know what is going into the plant, but something is going. But we ran the simulation. It is not a control problem, so that's why you cannot able to control. The purpose here is the x1 and x hat, the error between them should go to 0. Here I have selected different initial conditions. So you can see that from different initial conditions also it is coming to 0. And here also plant I have given as t as the initial condition, and the input as the estimator as 0. So due to this mismatch, there will be some error, but as time tends to infinity, this will go, both of them will converge. And this is the important feature of this particular unknown input observer. We don't know what is the unknown input, what is going into the plant, but just for the sake of, we assume that something is going, and we want to see whether we could able to estimate the same thing or not. So the blue one has gone to the plant, and you can see that after some time exactly it could able to estimate this disturbance as well. I have taken the second case as well. The second case I have considered the ramp disturbance, so unstable disturbance, so the ramp one, so it is going up. So you can see that this is the ramp. So since this is going up, there is no control action inside this one, u equal to 0. So obviously your system states will also go to 0. You can see that this particular state has going to 0. So this is x3 hat, the 3 states. So these 2 are going to 0. And due to the inherent stability of, could be the 2 eigenvalues of the plant are stable, unstable, and one is stable. So that's why this x1 is stable and the other 2 are unstable. You can see that I started with different initial values of the plant and disturbance. However, after certain time, both of them has converged. So this is what I would like to tell about the unknown input. So what I will going to give you now is, I will give you only this PDF file. I will not give you the skeleton code because you have enough experience in developing the things. If I keep on giving the same skeleton code to you, after the FDP, without the skeleton code, you can't able to do anything. So I will give you all this. This is the one what you have to build. You have to build on your own because these are just the gain blocks. The all blocks you can get it from this from the Simulink library, and this is the d by dt block. And this plant is given to you. This plant code is parameter file. First you have to run this parameter file, and this plant code, whatever you're seeing, you create your own m file, save it. And the disturbance observer also, what you are seeing here, just you can copy and paste here this one, and you build this one, and you try to build this one, and you build on your own and see if you can get the simulations or not. So for this, I'll be giving you the 45 minutes of the time. So it is around 7:40. So I'll be giving you 40 minutes or 45 minutes because it will take some time for you to go through this one, and then we will discuss what to do next. And then I will discuss about the papers. 2 papers I'll be discussing. One paper, exactly 2019 paper. It is not the very old one, and I will show you the concept, whatever you have learned, how they have applied, and how simple it is applied to particular that system, and how it got published IEEE transactions on, I think it is on smart grid. And another one is it's my paper, my own paper, and it is published in Automatica, so which is a quite good journal as far as the control systems are concerned. And there I have developed some new kind of unknown input observer as well, but it is a bit different from the existing one, and I will briefly discuss, throw some light on that paper as well, which is hardly a 2018 it got published, 1918 or 19. So that aspect also I'll be discussing. So what I will do is I will send you this this PowerPoint presentation. So you have to build this Simulink on your own. So for that I will be giving you around 40 to 45 minutes, and 40 minutes means 20 here, 20 here. So 8:20 we will be meeting again. by this time try to get all the results, whatever you are seeing here. Okay, so in another couple of minutes I will just send you this thing. So meanwhile, if you have any questions, you can ask. So because presenter sir, no voice. What do you mean by fault physically? Physically, the fault can be anything. If suppose if you are measuring your speed with some sensors, and if the sensor has some bias fault, that means instead of 10, if it is giving you 12, then that can be treated as one practical, fault. So as we keep on going, the things will get bit difficult, bit tougher. Just to ensure that after the workshop you can do on your own. Otherwise, it will be kind of spoon feeding, which I don't want to. That is not the purpose of this workshop. So you have to be on your own. So that's why slowly we have increased the complexity. First day you might feel it is very simple. Second day little bit difficult, and slowly we will increase the difficulty level. In another couple of minutes I'll be sending these slides. I try to cover as much as possible both the power electronics and power system to make both the communities happy. We discussed yesterday the combination of power electronics and power systems, that wind thing. But today this example will be power systems load frequency control. But you can extend it to any system. It is not that whatever the things you are learning here is only applicable to power systems or power electronics.
Hello, sir. Shivaram
Yeah,
here.
yes. Yeah,
Can I
please.
say this
Yeah.
disturbance
Yeah.
estimation as zero input response?
Disturbance input, yeah, this is a zero input response, yes. And due to there are two things here. There is an initial condition is also not zero here. So non-zero initial plant, at the same time the control input is zero, and this disturbance in some cases you can say that the unknown input, where the input control input is zero, but some additional input which is affecting your plant. So in general, if you see, there are two solutions of any particular solution, either due to the initial condition or due to the input. So control input is zero, but this you can treat it as some input which is going to the plant. Unknown input, you don't know about this.
Okay, sir. Thank you.
So if any of you have completed, the whatever I will be sending, if you could be able to complete before 8:20, you can go through the paper what I sent, and then we'll have the detailed discussion on that one. So just I sent this to my, because I want to send you the recent one with these things. So let me see if it has come to my mobile. I will send to WhatsApp directly. Yeah, it is there. Oh. So it will be in your WhatsApp. Yeah, it's sent. So it will be in your. You know, Anand Sarup has sent. Hemant has sent. So most of you are getting. Dr. Has some issues. Kusuma has some issues. I shared it. Nirmal, I will see. Yeah. Good. Yeah, already I sent. So now it is your turn to implement this one. And if you can implement this one, I can assure that the IEEE paper also you can implement with little bit if you put little bit more efforts. Yeah. So we'll meet at 8:20.
Hello, yes, sir. Hello, hello, sir. Hello, Hello.
Okay, so we will start our discussion now. 8:20 was the time, so I gave 1 more minute. My first question is, did any of you have obtained the results? Any of you? Please post it in either in GoToMeeting chat box or in the WhatsApp.
I think no, sir.
No one?
Nobody did post the result. I think.
It will take little bit time. Yeah.
Yes, sir. Yes,
Sir,
sir.
I'm Ravi speaking.
Yeah, Ravi.
There is a mismatch between these matrices, sir, that K and F. Matrix K and F. K is 3 by 2 and F is 3 by 3. And when you are adding this and the summer block, it is not matching there.
Okay.
And when I try to change the matrix size for F, and then C matrix has to be changed again.
Sir, is there any change done there in the sine wave increases?
Sorry?
What is the frequency or magnitude? Sine
It will
wave,
work for
what
any
we
frequency,
normally
sir. It will work for any frequency, any magnitude. It will work.
Okay. So, what the matrix dimension is mismatching. I don't know what is the problem.
I will see what is the problem. I'm just running the same code what I have given. I will see if there is any real issues. So this is the same code. Let me clear all everything. Now I will run the code, hard code which I gave you. All the variables A, C, E, F, K has come. And this is the symboling diagram. Hopefully it should run. If it is not running, then I might have given you the wrong file. It is the same code which I gave you is running now. I will show you the results, live results, so that you should believe me that whatever I gave you is the accurate one. It is initializing my code. You can see it is initializing here. It is running. It ran. I will show you the results, how it will look like. So this is the unknown input comparison, where you can see that how it is for the unstable system. I will change this to sinusoid signal. It is taking so much of time. Something got stuck, it seems. I will change it to sinusoid. I will not respond. Let it respond, because parallelly several applications are running in my desktop. So this is the comparison of, okay, the thing is my Google Drive is getting updated, so that's why. Now you can see that I have changed to sine signal, and the frequency I set it as 10 radian per second, and if I'm running, It is backing up all the unsaved data because that's what I gave. That option I kept compiling. It is running. This you can see that this is the unknown input of the frequency of 10 hertz. You can see that after certain time, almost the disturbance has one can see the disturbance. And now what I will do is just for the sake of thing, I will give very high frequency. Let's say I'm giving the 100 radian per second, and I don't want to see for 10 10 seconds. I'll set it to 1 second, and you can see that the system response is slow. That's why it couldn't able to do that one. To get the faster response, you have to choose the faster gain values, k values very fast in one of the things. So there is a trade-off. If you want very fast signals to estimate, then you need faster this thing. Otherwise, we will see if I run it for 10 seconds whether it would able to do it or not. If it is not, yeah, you can see that it took some time. It took around 5 seconds, and then it slowly it started. You can see that estimation is happening. So it took
Sir,
some
what
more
is
time.
delta
So
U by delta T block, sir?
it is a differentiator block,
Sir,
sir.
delta U
Yeah, this is the
actually
derivative. I took the photo and I sent it to you as well, sir. Numerical derivative block. The same.
numerical derivative. Where we can
Yeah,
get this one, sir?
I will tell you, sir. So this actually, the problem with the derivative thing is what we discussed in the earlier thing. Even if you are using the PI controller, or we limit ourselves to PI controller, not to PID controller, because of the actual derivative will have its own noise phenomena. So we told that how to do this one, the practical, like by tau into 1 plus tau is something we discussed. The same things is coming here. The same. You can search the numerical derivative in this toolbox in this search engine. If you search, it will show up, sir. Otherwise, you can use the simple d by dt as well. I will show you the simple d by dt. Derivative block. You can see this one's a derivative block. Yeah, this is the derivative block, sir. The same simple d by dt. In various versions, there are different d by dt's. So derivative blocks, you go here, go to the continuous. The first block is the derivative block. Okay, so now what we will do here is now we will discuss on paper, two different papers. I will show you the first paper here. This is two-stage information filters for single and multi-sensors. So TSIF, we generally say is two-stage information filters for multiple sensor and disk varied versions. So why this paper is relevant to the work what we have discussed here is I will show you. Yeah, this is the dynamics, discrete dynamics we have considered, where the plant is perturbed. Here you can see that this perturbation what we discussed is 0. So this is the process noise, and this is a measurement noise, so which we have not considered till now. And the another thing is this F into P. This is kind of a bias or fault, and we developed this for not only for the single set of sensors. So if the information is coming from multi sensors, and if you want to fuse to get the optimal data, then generally we use the information filters, and we have developed this two-stage information filters for this fault estimation or the bias estimation. This bias we just named it as a bias. We are telling it as a bias. Some people say it is a fault, some people say it is uncertainty disturbance and other things. So we developed this one. So the numerical part may not be of much interest because it is highly numerically intense, which I will not go into this one. But the results, you can see that we have considered various real systems, real life uncertainties as well. Like the system is well conditioned, and if the system is ill conditioned, then what to do. So that aspect we did several analysis. So you can see that when the system that bias is 0, that means there is no fault. then estimate is also fine. And you can see that a lot of noise. This is noise is because of the realistic sensor noise and process noise what we added here. So my bias is 0, everything is bias is 0. You can see that it has worked for both ill conditioned system and the well conditioned system. And the second thing is we have used the quadruple tank model. So here we have given the step input as the actual bias. You can see that very fine. It can able to estimate in all the cases with multiple sensors as well. So what we have used that to measure the same particular stats, we have used two different types of sensors, and we try to fuse the information to get the optimal data. So this multiple sensor information, multiple sensors getting the data is very much essential for various purposes. For example, if you consider the ISRO's applications or NASA's applications, where what happens is if you want to track the location of the re-entry vehicle which is entering to the atmosphere from after doing certain operations in the space. So once if it re-enters to the atmosphere, the position is very much important. The position, location, the positions, and other the states of the particular re-entry vehicle is very much important. So for that re-entry vehicle, so generally what they do is they place the radars at various locations, various altitudes, and from various altitudes, wherever the data from the radars, they fuse at some centralized facility, and then they try to get the optimized state estimate or the optimized location of the where your re-entry launch vehicle is there, re-entry vehicle. So that is one such application, and in more people can use it for synthetic vision as well. That means you can use the combination of cameras and lasers and so on to detect a particular obstacle in the day or night, and you can fuse the data from both. If it is not completely dark, you can use the information from both the cameras as well as the lasers to detect your obstacle. And so that is another such application of this multi-sensors, which I will not go into. So the purpose here is so we have proposed something which is quite a bit advanced than what we have discussed, unknown input observer. This is also kind of unknown input observer, but here it can deal with multiple sensors, and it can we have proposed a squared version so that it can deal with realistic, really if your system is ill conditioned. Ill conditioned means if your system eigenvalues are completely very far away from each other. Suppose if one pole is located at 10 to the power 20, that is very far, minus 10 to the power 20, and another pole is located at 1. So you can see that it is highly ill conditioned because the ratio of the maximum eigenvalue to the minimum eigenvalue is very large. So during those conditions, one has to be very cautious. So we proposed some kind of squared versions as well. So this is one paper which is may not be of much interest. So this paper is the recent one. As I told, this is the 2019 paper. So deterministic dynamic state estimation based. See here they are using the deterministic. That means they are not using any sensor noise, or your system is not stochastic. It is deterministic. Dynamic state estimation based optimal LFC of interconnected power system using unknown input observer. So here they have used the unknown input observer for the state estimation of the optimal LFC. So this literature review is completely shit. We will not go through that one. So yeah, so this is the plant. So this is the plant what they have considered: delta Fi, delta PGI, and delta XGI. This I means for various areas they might have taken. Uh, so this is the thing what we have already seen. If I zoom this one, you can see that this is very much known to us. So similar thing we have discussed: turbine, governor, and rather we have not used the GRC heater. We have not used, but similar two area systems we have two area power systems we have discussed. So the structure of this particular plant looks very much similar. So you can see that there are unknown inputs, control signal, unknown models, known output. So the measurement is known. So model is unknown, control signal is known, and the inputs, this red one which are going to, these are the disturbance. So unknown inputs. So this is the actual thing what you have done. So this is the same structure what they have used. So x hat equal to combination of y into h plus z, and t into b and f into other things. So in our case, what the simulations the input is 0, so that's why we assume that this particular channel is 0. And the same thing, the same equations what we discussed here, the equation is the same because he has taken the information from the same. So here what he is using is 1, 2, 3, 4, 5, 6, sixth order plant, and one is the input. Input is only one plant input, whereas two disturbances, are affecting the system. So they have designed the unknown input for each power area, and this is if you remember, this is the exactly structure what we discussed, and this is the array dynamics e dot how it is coming, and this is the selection of the various constants what we have seen, and if you select this, it will ensure e dot equal to fe, provided this f you have to select as a stable, and this is the same the disturbance observer what we have seen and what we have designed. So this is unknown input. So various mathematical analysis they have done, which is of not much use, stability and other things. If you are interested in finding these things, the control law what you have used is the LQR control law, straightforward LQR control law. In our case, the control law is 0, u equal to 0. So they have used the LQR here, and so you can see the control law whatever here they have used. It is based upon estimated states. In general, we have discussed the LQG, where the combination of LQR and Kalman filter, but here they have used the LQR as the controller and unknown input UIO as the estimator for the states as well as for the disturbance. And they have done the simulation, and different values are given here, Q and R values, and different parameters are also given here. And this is what their results. These are the state, various state estimations how it is happening. This is the error. So you can see that both state and estimators are doing very good. But for the practical reasons, if this paper comes to me, I might reject or I might be the major reason, because here you can see that the real and estimated state, they have assumed it as the same. So the initial condition are the same. But in general, for the practical systems, the initial conditions you don't know. So it should be your observer or the controller work for a different set of initial conditions as well. But here, unfortunately, he has taken the same initial conditions, if I'm not wrong. Otherwise, I have to go into much details. And here you can see that what is happening for various scenarios. And they have done the investigation for various things, various types of simulations they have done, and various frequency deviation and all other for various cases they have seen, various faults they have estimated, faults and other things. And here they have compared with the proposed and with PID and CO and LO, Leuven Berger observer, I think LO, and they have shown that the response is very good. And here are the parameters, all the parameters here you can see. So what I can say that all the ingredients required for this paper we have already discussed. We have discussed the two area systems, so their model is more or less very similar. We have discussed the LQR, how to design the LQR for various problems, so that is also known. And we have discussed how to how to design the unknown input observer, so that is also known to us. So if we combine all three of them, then that becomes paper. So that's it from my side. So as I told, it is 8:45. I'm going to wind up. So another five minutes we can have the discussion, and if you have any more discussions, we can. You're always welcome.
Sir,
Yeah,
Sir.
Dhananjay.
This is Dhananjay from NIT Raipur.
Yeah.
Sir, actually, in this paper, I think
Yeah.
the unknowns they are assumed unknown
Mhm.
inputs. I think
They have not assumed,
they
sir.
took unknown. They are not estimated. They are not estimated. Only they assumed some unknown input. They are given to plant. I think. In this system.
I think the estimation also has been done, because they are mentioning here, this estimation formula they have given. So what I assume that since the disturbance, they might have estimated as well. So that we can
Said,
go
sir,
into the details.
one line they wrote that there are. One line
It
they
can be
wrote that
done.
power fluctuations, load fluctuations, and renewable variations are modeled by and modeled as an unknown input to the power system operator. They
Okay,
model
fine.
these
So they have
three
not.
variables. They assume
So
some
delta
unknown
F.
inputs. From there, they are estimating the state. Actually, I think in this.
No, here you can see the delta. What is the delta P's are the the unknown input, right?
Yeah,
Let me
delta.
delta PD and delta P tie are the unknown inputs. Delta PD and delta PI.
Delta P tie.
Even if they are not estimating, also estimation doing is not a big problem. Only one line code will estimate. That's what we have seen. You try to estimate, then you try to
But
give some.
their motto is not the estimation, I think.
Fine,
I think
fine.
their aim is
I mean,
not to estimate that.
yeah.
I think they assume some unknown input. From there, they are showing that even in the presence
Yeah.
of unknown input, also my state it is accurate estimating the state some kind of thing
Yes.
there.
Yeah, that is because they have done everything. If they, if they do that unknown input estimation as well, that will also be the good. But they are not done. That is fine. Yeah. So, but they can do it easily.
Yeah, exactly.
It is only
Yeah.
a single line code will do that. So that's what we have.
Yeah.
Okay. Maybe you people can do it, right? You know how to estimate it. You give some, certainty, give some step. Already they have given the step. Just whether you could able to reconstruct that unknown input or not.
System that has external
Hello, sir.
disturbance can we go for this one, sir?
Sorry, your voice is not audible.
So any system that has external disturbance,
Yeah,
can we
you
apply
can go
this
for it.
UI?
Of course, but only thing is the rank it should satisfy. Rank of C and rank of C should be the same. There are some mathematical intelligence which I have not discussed just to avoid too much of maths in this particular lecture.
Okay, sir.
Tomorrow is setting controller.
Okay.
Yeah. Anything else? I will be activating the queues now.
Hello, sir.
Still 2 minutes are there. Yeah.
Sir, your paper is there, sir, square root version.
Yeah.
Sir, how do you implement it? Could you explain?
How do I implement it means? Okay, let me go through my square root paper. I think I closed that one. Just let me stop this and I will see. Our initial, I will be answering that question. Our initial conditions in all the integrated simple zero or anything else. You can give different initial conditions, and you can see what is happening. It should work. Not only zero, it should work for any initial conditions. If initial conditions are very far away from each other, very far away the actual and estimated, then it will take a little bit more time. That's it. Otherwise, it should work for for all such kind of things. And somebody has asked what is the difference between where is that one? Yeah, the difference between the fault uncertainty and disturbance. So generally, in general, as far as the robust control terminology is concerned, uh, robust control terminology is concerned, the faults, the disturbances are the slow varying things, slow varying signals. We generally call it as a disturbance, and the slow varying is low frequency, and the high frequency signals we call it as a noise. And there is a mixed sensitivity approach in robust control to deal to based upon the frequency spread. We can go for two different types of strategies, which is called as a mixed sensitivity. In the low frequency, we try to achieve some specification in the high frequency, and that is but uncertainty can be can come from various aspects. The plant is Krishna Jyoti. Could you please be on mute? Thank you. I can say that the uncertain plant means if you are A matrix, B matrix, C matrix, or D matrix, if there is a change in that matrices, generally A plus delta A we consider. A is a nominal and delta A are the variations in that one. That we call it as an uncertain plant. Uncertainty in general, that is a parametric uncertainty we call. Uncertainty can come from various aspects, other aspects as well. And the faults, generally there are many types of faults possible for a practical system. I will show you how many faults are possible. We have done something, but before that, let me activate the quiz because it is 8:45. So those who are interested, they can stay here for the discussion. I have activated the quiz, and yeah, and I will tell you that there are many ways of looking the faults for the real Airbus aircraft. The bias fault, the sensor faults, actuator faults. Again, in the fault itself, there are very things. Diverging fault, converging fault. There are many types of faults possible. All such faults, your observer should able to estimate all such faults. So, just for practical reason, I have shown you how to estimate one oscillatory sinusoid fault, and the other one is the unstable fault, which is the RAM. And yeah, let me see any other questions if somebody has raised.
Sir, hello.
Yeah, hello.
Sir, what is the example of divergent fault? Just you told that divergent fault.
Divergent fault. Suppose if your sensor has failed. Suppose if
Sensor
your
is
sensor has
fault.
come. Yeah, if its sensor has completely failed. So what will happen? Nothing is going to the plant. Okay. Let us assume
Okay.
only one sensor. It is a speed sensor. If the sensor has faulty, failed. So what is going to the plant? Zero. Zero is going. So what will happen? If zero is going to the thing, even though if there is some speed of the motor, due to the sensor failure, what is going to happen? Your control will automatically keep on increasing. If the system is unstable, if it is, your control will not act because the feedback loop has been broken. The sensor there is fault. So that fault keep on increasing. So that is called as a diverging fault. That is an example of a diverging fault.
But sir, for that backup is there or not? Backup
Sorry?
protection. Backup relay is there or not?
That depends. That depends if you are using the redundant sensors or not. If all the redundant sensors are failed, then what you will do? I will tell you one such practical case for the Airbus system. What they were using the redundant, triple redundant for the angle of attack sensors. What happened is, unfortunately, due to the icing means it was very cold, -degrees. So all the three sensors got stuck. So the pilot, what he was assuming that whatever the sensed information, whatever is getting from the sensor is accurate, but it was faulty because the ice has blocked. Due to the icing, it has blocked, and the pilot has thought in the other way. It was going down. He was thinking that it was going up because of the lack of things, and it was not completely visual, and some other sensor also failed, and it got it crashed. So that tells it was a simple control. It was not a fault tolerant control. So that gives an opportunity, that gave us an opportunity to explore that one. And Airbus has funded the project through European EPFP7 frame point 7, and they have given that to some 12 universities, and that is called as a reconfigure project to solve that small problem. Although it is a very small problem, but they have they have funded hundreds of crores to 12 institute and research institute in the Europe, including Oxford, Cambridge, the Exeter, and some DLR, NLR, some German and the Netherlands space agency, Dutch agencies as well.
Sir, if you are telling that this condition, no control action will be there, no control will work. If that
Controllers are there, but they are not fault tolerant controls. They were using the simple PI controllers or simple some control techniques, but it was not a fault tolerant control. If it is a fault tolerant control, then yes,
then it will work.
yeah, it will work, of course. So we have shown that with this fault detection algorithm, if you know the fault information, how to give the different control signals, how to get the desired control signal also was of our interest. So we have done that one.
Okay, thank you, sir.
I have activated the queues. Those who are interested, they can they can
Hello, sir.
join.
This is
Yeah,
Hamchandar.
yeah. Hi.
Sir, once can you show me the Simulink model of the previous one? Because in your system it was running fine, but we don't know what the problem is. Almost, I think
I
everyone of us has the same problem.
I know what could be the problem is, but you have to
Clock.
work hard.
We
I
did
will
not.
show you. I will show you. I will show you what is it.
Yeah, we did not keep the clock. That might be the problem, is what I assume.
No. Clock is just for the time purpose, nothing. So I'm
Okay.
just sharing you my.
Yes, it is. Thank you.
Yeah, this is what This is same thing. The same screenshot I have sent to you. Nothing more than that.
Yes, sir.
I will give you the hint. I'll give you the hint. So why it is not working? You please check all, double click, and please check the settings of all these blocks. It should work. I know what mistake all are doing, but I don't want to tell you the mistake. The hint is double click each of the blocks and check with different settings, then it should work.
Integrator initial conditions you need to keep, no?
I cannot tell. Then you think of it that one.
Already it
I'm
is run,
telling
sir.
one. Huh? Yeah, fine. Then that is fine. Okay, so
the matrices,
there are,
matrix into U, I have already changed it into matrix into U. It's not working.
it will work, Ravi. It will work. It will take some time. You have to debug. Everything is correct. The code I gave you the correct. The simulating diagram I gave you the correct. It is working here. I have shown you for any kind of things. So now it is your turn to see.
Okay, sir. Okay.
Just that's why I have not given you the skeleton. Why I have not given you the skeleton? If I give the skeleton, just you follow the skeleton. All of you just copy and paste. It will work fine. But that's not the thing. What I want. I want you to be on your own from now. The next thing will be a bit more difficult. Backstepping. So slowly, if you see the difficulty level. So you try this one. The problem, you check all the blocks and see what is happening. That's what I can tell.
Okay, sir. Okay.
Let me see chat box if anyone has said something. I am asking with respect to simulation or initial condition and all that you have to think. If it can be, from the results what I have sent to you, the slides. In that slide, if you see the figures, from that you should make out what are the initial conditions I have used. It is nothing but 1, 2, 3. I use the initial condition for the plant, and I use the 0 for estimator. So I gave you this answer as well. Banu, this was Banu. Yeah, got it. Is it possible to make the estimation error time to control? Example, if estimation error less than 5 in the, yes, you can make it. The only thing is you have to, the k value, whatever I have selected, if you go through the literature, then I have selected the poles as -1, -2, -k. If I change the poles location to -10, -20, -30, yes, you can make it the convergence fast. I could not complete because of an issue with MATLAB and my laptop. Okay, no, sir, there is an issue in the input side. Yeah, you guys, now you have to, slog hard to sort out these issues. You will get it. I know you will get it. Just be patient. Have patience. Go through each block and try giving different blocks, so that will be the learning. And see the older, the MATLAB files what I have given, what I kept inside that one. So everything, all the basic ingredients required to cook biryani has been given to you. Recipe has also been given to you. Now it is your turn to try and let the biryani get burnt first time, second time, third time, and later on, you will enjoy the taste. So tomorrow we'll be discussing the backstepping controller. We will go through one research paper, and then we'll try to how to solve that research paper, how to apply the concepts what we are going to learn. And tomorrow I will not give you that this simulating diagram. Simulating diagram I will give you inside the blocks. You have to write your own code tomorrow with little bit skeleton. I will give very little small things. So that's the way what I'm planning for tomorrow. And day after tomorrow is the last one, right? Yeah. So what are the topics we are left with? Backstepping and the extended Kalman filter. So tomorrow I will try to cover both the topics, whereas in the last day you'll get an opportunity to have to revise the things and cover anything else if it is possible.
Hello, sir. Hello. Hello, sir.
Yeah, yeah.
Sir, could you please
Hello?
explain your paper?
Okay,
Could you
my
please
paper.
explain
Okay,
your paper?
okay, okay. Before, yeah, I explain that paper. Where is that paper? Which is
How do you find the square root?
I will explain, but it will be very new, mathematically very intense. But I will just give you the flavor of what is it about. Yeah, this is the paper, and so this is the bias. This is until this it is standard in the literature. So which was proposed in long time 1997 and so on. And two-stage filters or information filters were also proposed, but they have not proposed for the fault estimation. We proposed for two-stage information filter. So basically, it will be having parallelly we are estimating the bias in information filter and with bias, and then later on we are combining both the knowledge to get the combined TSIF two-stage information filter. The same thing what you have seen in the unknown input observer as well. Two different filters are working parallelly. You can see that Z is working parallelly and X is working parallelly, and then you are combining Z and X to get the desired answers. So why I'm saying the square root is here, instead of propagating the covariances, I'm propagating the square root of the covariances or the information matrix. So that will have an added advantage over the numerical stability. Suppose numerical stable things. Suppose if your processor has the limited, if it has limited capability, then the square root will ensure the double precision. Suppose if your computer or the processor can see up to only 3 decimal places, I assume that up to 3 decimal places. In normal, it cannot able to see the more smaller than the 3 decimal places if it is fourth decimal place or the fifth. So by this square root information filter, automatically it can see up to the twice. Although it is only if your process is up to see up to 3 itself, but inherently it can deal up to 6 decimal places as. So that's why the square root information. So square root of the particular covariance matrices we are trying to propagate. So again, for that, I mean, it is lots of maths are involved in this one, and we have used QR decomposition, and we have used the J unitary transformation for to decompose the matrices, and to ensure sometimes the positive definite matrices should not lose their properties, and all other things have been considered here. Yeah, this is the one.
Hello. Hello.
And yeah,
How do we find the square root in MATLAB? We have to use a QR decomposition.
sorry,
We have to use a
your voice is not clear, Ashwin.
Hello. I will text, sir. I will text.
Yeah. And this is the what I was telling you, different various types of faults. What I think my screen is not shared. I will show you that one. How to consider the various types of faults. And this is the whole operating region of the aircraft with altitude 13 kilometers to 305 meters, and various options, various gears when it is on, and for various, these are around 222 operating points. And we have verified, so this is the reconstruction. This is alpha fault, and we have reconstructed, and we assume that some of the parameters are also imperfect. and that is for the linear parameter varying system. So this is the aircraft pitch deflection, and for all 222 plots is that one. And this is the reconstruction of one of such things. Yeah, so various types of faults has been considered here. We have done the testing. And it was implemented, they have tested on the crash data as well, so real data, and it works fine. And whatever the results you are seeing, it is actually on the not on the simple numerical model. So this data has been captured from the aircraft crash black box data, and we have implemented and we have tested. This has been tested in that. Okay, so now this is 9 o'clock. So so I'll be,
So can you
so
please
if you
share?
have any queries. Sorry. Hello.
Can you please share the paper that robust model based fault diagnostics for dynamic system?
Oh, that IEEE paper? You mean to say that IEEE paper?
Not so Springer Science and Business Media 2012. That is representing UI theory in the slides.
No, that is the slides. Let me see.
Because we will be needing initial conditions.
This one is the textbook, sir. This one is the textbook. Actually, this is a textbook. It is not the paper. It is a textbook.
Okay, in the Simulink, how do we get the initial conditions, sir? I mean, for the
Simulink,
model.
in the you can just double click that one. Double click, and there is a there. By default, it is 0. You can give different initial conditions there.
So we can give any value to that, or?
Yeah, it is up to you. Suppose if it is a brushless DC motor, let us assume you don't know what is the initial rotor position. Rotor position you cannot exactly fix at 0, and you can run the motor. So it should work for any non-zero initial conditions. Suppose, for example, if it is an electrical circuit, suppose initially the capacitors are charged or inductors are charged, so there will be some initial charge in that one. So during those cases, you have to give some initial conditions to see the realistic effect for the system. So that is based upon the problem at hand. This book, coming back to your question on this book is not available. Rather, the thesis of Chen is available. So it is exactly the copy. Thus, I can share you the link for this Chen's thesis. So exactly the same thing is in the book as well. That I will share you that Chen and Patton's their thesis. It is there. I will share you that link. So I think it is the chapter number 3 where unknown input observers has been discussed in very detail. In fact, this is available online also, because it is ethically wrong if I tell you to download from online. So if you are interested, there are many sources you can download this online. There are many websites. This textbook is available there. But I will share you the thesis which is available online. So thank you all. So if you have any queries, we can discuss tomorrow. So this is the end of the session. So by tomorrow, what I expect is at least try to complete the simulations of the file of the PDF what I sent. And the second thing is, if possible, you try to do some simulations on the paper that LFC, load frequency control. And yeah, we'll be discussing the backstepping controller tomorrow. Thank you all. That's it from my side.